Good morning, everyone. Uh, so today we will start our discussion on LL1 parsing. In the last class, we have seen the design of recursive descent parsers, top-down recursive descent parsers. So you are given a string W. We want to check if this string W is described by the grammar G. Okay, that is, in other words, whether the string belongs to the language described by the grammar G. That is the question we are trying to answer. Okay. And there are two parsing approaches we have mentioned. One is top-down parsing, the other is bottom-up parsing. Right now, our focus is on top-down parsing. So the approach that we have seen in the last class is this. We start with the start symbol S. Okay, we start with the start symbol S. And so from that point, we would like to construct a derivation which takes us to the string W. And what is this process of derivation? So in terms of parse tree, we start with S and we keep expanding the parse tree. Let's say from S we have, let me, so starting from start symbol S, so far we are able to generate this intermediate left sentential form. Okay. Remember, in top-down parsing, so when we are trying to expand a non-terminal symbol from a intermediate form, intermediate sentential form, we pick the leftmost non-terminal symbol. Okay. So for example, here, if the intermediate form is UA alpha, we pick the leftmost non-terminal symbol. And U is a string over terminal symbols. And alpha is a string over terminal and non-terminal symbols. Okay, A is a non-terminal symbol, U is a string of terminal symbols, and alpha is a string over terminal and non-terminal symbols. In the process of derivation, in the top-down parsing, we pick the leftmost non-terminal symbol and expand that non-terminal symbol. Okay, so we are at step 3 now. Pick the leftmost leaf node, which is labeled by a non-terminal symbol. And we would like to expand that non-terminal symbol A by applying one of the substitution rules. Like for example, A may have two substitution rules, A going to alpha or alpha 2. So we put the substitution rule, A goes to alpha 1, and we expand the parse tree. It can be a success or it can lead to a failure. So when do we say it leads to a failure? From A, if we generate a terminal string V, okay, if we generate a terminal string V, and V is not a prefix of the rest of the input which the parser has to consume. Remember, we are parsing, so we are trying to check whether W, the input string, is a valid string described by the context-free grammar. So, and so far we are able to generate the prefix U, okay, and Y is the suffix that we want to generate. So in the process of derivation, so we use the substitution rule, A goes to alpha 1, and we have generated a prefix V. So Y should be a prefix of the rest of the string Y, that is, Y should be of the form V, Y prime. Okay. If this is not the case, then we have to backtrack. So instead of using the substitution rule, A goes to alpha 1, we have to use the substitution rule, A goes to alpha 2, and try if we can generate a prefix of the input string. If we can generate a prefix of the leftover string Y. And if even after using the second substitution rule, A goes to alpha 2, if we are not successful, then we say that there is a parsing error. That is, W does not belong to the string, does not belong to the language described by the context-free grammar G. That is, you try the substitution rule A goes to alpha 1, you try to use the substitution rule A goes to alpha 2, neither of them works, in which case you don't have any other remaining option. So you declare that the input string W is not a valid string described by the context-free grammar. So here is the thing. So if there is an input mismatch, okay, backtrack and try another production. So this is the strategy in the top-down recursive parsing. This is the approach that we have seen in the last class. So we will refine this approach further and see how we can eliminate backtracking in today's lecture. But before we go further, so there is one important thing that we have seen that, like for example, if you consider the grammar on the top left-hand side, and let's say if the input is ID plus ID, and if you want to apply recursive descent parsing to check if the string ID plus ID is a valid string described by the context-free grammar, we get into trouble because we use the substitution rule E goes to E plus T, and then again we use the substitution rule E goes to E plus T, so on and so forth, and the recursion never ends. Okay, so we get into an infinite left recursion. So this grammar, the grammar that is there on the top left hand side, it is not amenable for top-down parsing. Okay, so what we do is we take that grammar and rewrite that grammar by eliminating the left recursion. In the last class, we have seen a strategy for eliminating left recursion, and the grammar that is obtained after eliminating the left recursion is what you are seeing on the bottom right hand side. Okay, so we will be using the grammar on the bottom right hand side for today's class and even in the next class. So you have to get some intuition about this grammar, what this grammar is doing. So in order to get that intuition, let's try to see how the derivation process will be like on an example input string. So let's say you start with E. So when you are you use TE prime, and then so by using the first substitution rule, we have generated one term. Let's say using E prime, we get this intermediate form. So what you can see is by using the non-terminal symbol E prime, we can generate sum of terms. Remember our expression, the way we think about our expression grammar is an expression is sum of terms. By using the substitution rules corresponding to line 1 and line 2, we will be able to generate sum of terms, okay, where sum means plus or minus. So now let's say, and each term, it's a product of factors. So what we can do is going to the next line. So the first term is ft prime plus te prime. So let's use so I want you to focus here, okay? Using that non-terminal symbol t prime, we can generate product of factors. An expression is sum of terms. A term is a product of factors, where product means a product can involve star or division operation, okay? This is what we have so far. So now let's go to the next level. So this is level 1, maybe we can call. This is level 2, where we are generating product terms. And then finally, in the last level, let's say this is level 2, where we are generating product terms. In the last level, we want to generate the actual factors. What is a factor? A factor can be an identifier. So you replace this F with identifier, star, and this factor also with identifier, and T prime. You don't want to generate any more factors, so you replace this T prime with epsilon symbol, okay? And then we are left with TE prime, the next. So again, what you do is id star term is ft prime e prime id star id, and this factor we replace it with id, t prime we replace it with epsilon, e prime we replace it with epsilon. So this is how we can generate a string such as id star plus id using the grammar where there is no left recursion present. I want you to understand this grammar and try to gain intuition about this grammar, because we will be using this grammar for the rest of the discussion on LL1 parsing. Let's keep going. So what is our goal? Our goal is we want to see that we will be able to expand the parse tree or construct the parse tree for a given input string without backtracking. Okay, so we want to construct the derivation starting from the start symbol S to W, or in other words, we want to construct the parse tree associated with this is all W associated with the string W without backtracking. So what is the idea here? So this is the situation in which we are in. So from S, we have generated U A alpha, and W is U A V. So this prefix V is already generated. The next input symbol is A. So we want to, and A has two substitution rules. A goes to alpha 1 or alpha 2. So the idea is we want to use the lookahead symbol. What is the current lookahead symbol? That is the terminal symbol A. We want to use the current lookahead symbol to decide whether we can use, whether we should be using the substitution rule A goes to alpha 1 or A goes to alpha 2. So that is the idea. So let's try to understand this idea that how we can eliminate backtracking by using lookahead symbols using a series of examples. So let's take the first example here. Okay, so this is the example that we are looking at. Okay, so during the time of parsing, so let's say if the next input symbol is 0, okay, if the next input symbol is 0, then, and if the current non-terminal symbol to expand, so if you observe, there is only one non-terminal symbol here, that is S. If the current non-terminal symbol to expand is S, and if the current input symbol or the lookahead symbol is 0, we can go ahead and use this substitution rule. On the contrary, if the current input symbol, is 1, then we can go ahead and use the second substitution rule. Okay, so that is, if the input is looking like this, W is equal to U0V. This is the current symbol. Okay, so if the current input symbol is 0, use the substitution rule 1, and if the current input symbol is 1, use the substitution rule 2. So here we are able to deterministically pick whether we should be using the substitution rule 1 or substitution rule 2 by using one lookahead symbol. That is, K is equal to 1. K is the number of lookahead symbols. So now when we go to the second example, this is the second example. So again, we have three substitution rules here. So if the current lookahead symbol is 1, then we will not be able to say whether we should be using the substitution rule 1 or 2. This is the substitution rule 1. This is the substitution rule 2. So we will not be able to say whether we should be using the substitution rule 1 or 2 by looking at the current lookahead symbol. But if you are permitted to use two lookahead symbols, then we can say if the next two symbols are 1, 1, then we can use the substitution rule 1. And if the next two input symbols are 1, 0, then we can use the substitution rule 2. So again, the idea here is by using two lookahead symbols, we will be able to eliminate backtracking. So now coming to example 3. So this example 3 is a very simple example, but it's very interesting. So if the next input symbol is 0, okay, use the substitution rule 1. If the next input symbol is 1, use the substitution rule 2. If the next input symbol is C, use the third substitution rule. So this is the idea. So again, by using with one k is equal to 1, that is with one lookahead symbol, we will be able to eliminate backtracking. So from this, you can kind of get intuition on how we can parse programming languages using this idea of lookahead. Like for example, if the next keyword is for, then you can use a substitution rule which generates a for statement. If the next input symbol is a while keyword, then what do you do? Or if the next input token is a while keyword, then you may want to use the substitution rule which corresponds to a while statement. If the next input symbol or if the next token in the input is a do keyword, then you may want to use a substitution rule which corresponds to the do statement. Okay. So by using the next lookahead symbol, we can deterministically pick one of the available substitution rules for expansion. Example 4, which looks very simple, is kind of bit tricky. So is it possible for us to come up with a backtrack-free parser, for example, for grammar? Okay, this is the grammar on which we are looking at right now. So the problem here is if the next input symbol is 0, we would like to use the substitution rule 1. If the next input symbol is 1, we would like to use the substitution rule 2. Then when would you use the substitution rule epsilon? Okay, so this is a tricky question. Okay, so this substitution rule, when do you use? In order to understand this, let's consider a string 0, 1, 1, 0. This is the string that we have. And yeah, let's see if this is a valid string generated. Yeah, I think let's take a different string. So I want to take a string which is present in the language. Okay. 0, 1, 0. Great. So this is a string which is present in the language. Okay. So let's see how the derivation process happens for W. So you start with the start symbol S. The next input symbol is, the first input symbol is 0. So you use the substitution rule 0, S, 1. So now this 0 here matches the current input symbol 0. So success, you go to the next input symbol. The next input symbol is 1. So you want to use the substitution rule 1, S, 0. So now this 1 matches the current input symbol. So you advance the input pointer here. So the current input pointer is 0. So you want to use the substitution rule 0, S, 1. And then this 0 matches this 0. So you want to advance the pointer to the next input symbol. And so the next input symbol is 1. So you want to use this production 1s0. So as you can see, the parse tree that we are constructing does not correspond to the parse tree associated with the string W, because we are using the incorrect substitution rule in the process of constructing the parse tree. Let me use because at this point, so instead of using this substitution rule, we want to use the substitution rule S goes to epsilon. If we use the substitution rule S goes to epsilon, then the derivation process will go successfully. But then we are not sure. So what is the guiding factor? How do we know that we should be using the substitution rule S goes to epsilon? Okay, so this is a problem. So we will revisit this grammar again towards the end of today's class. Now let's move on to example 5. So is it possible for us to come up with a backtrack-free parser using some constant number of lookahead symbols? for example 5 grammar. Okay. So if you look at example 5, there are a couple of things. Okay, so from ACE, there are two substitution rules. So one substitution rule will result in the generation of a terminal symbol E in the string, and another substitution rule result in the generation of the terminal symbol F in the string. So put it other way, if the input string contains E, then we should be using the first substitution rule. And if the input string contains F, then we should be using the second substitution rule. Okay. But the problem is given a string W. So let's say if you are using the number of lookahead symbols that you are using is 100. So if you use 100 lookahead symbols, so you may have a binary string of length 100 or no whatever, some string, binary string of whose length is greater than 100. Followed by that you may have E, and followed by that you may have some binary string. Okay. So in this case, so no matter how many lookahead symbols that you use, E could be appearing farther down in the string W, in a particular string W, and you will not be able to deterministically pick whether you should be using the substitution rule 1 or the substitution rule 2. So now let's look at example 6. Example 6 is a language with over a unary alphabet. That is, the alphabet consists of only one symbol. So the question for you, I will not be answering this question. So I want you to uh, check on these two questions later on. The first question is, what is the language described by this grammar? The second question is it possible to come up with a backtrack-free parser for the language described by this grammar? So question 1 is, what is the language described by this grammar? And question 2 is it possible to come up with a backtrack-free parsing strategy? And now let's look at example 7. So if you look at example 7, if the current input symbol is A, then we can use the substitution rule 1. And if the current input symbol is 1, then we can use the substitution rule 2. But one thing that we have to appreciate here is, just by looking at the substitution rules associated with the symbol S, we will not be able to say whether we should be using the substitution rule 1 or substitution rule 2. We have to go one level below and see what are the kinds of strings that are generated by the non-terminal symbol A, and what are the kinds of strings that are generated by the non-terminal symbol B. And we have to use this information to go one to say whether we should be using the substitution rule 1 or 2. Great. Let's see if you have any questions. So there is a question on ambiguity. What about ambiguity? In that case, do we consider any valid parse tree for a backtrack-free derivation? So when we were discussing this idea of ambiguity, so we mentioned when we are so there are two ways of handling ambiguity. One way of handling ambiguity is by grammar transformation. Another way of handling with ambiguity is you tell the parsing algorithm to always lean towards one particular kind of parse trees. And and we would like to come up with a backtrack-free parser to construct parse trees, towards which we are leaning towards. Okay, let's say, like when we are constructing parse trees for expressions involving addition, we want to lean towards parse trees where left associative property is respected. So when we want to construct parse trees in a backtrack-free approach, so the idea is the same. We want to construct a parse tree which respects left associativity, and we would like to construct it without doing backtracking. Another question: will example 3 grammar suffer from the same problem as one in example 4? I want you to think about it. So let's think of it as a homework problem. So compare and contrast the grammars in example 3 and example 4. We have seen the problem associated with example 4 grammar, and I would like you to check whether a similar problem exists for example 3 grammar also. So there is another question, the grammar where we are looking at the first look ahead symbol, is that LALR grammar? We will talk about LALR grammars later on, Apurva. Let's keep going. Yeah, now this is the grammar which, this is the expression grammar which is obtained after eliminating left recursion from the original expression grammar we started. And the question is, can we construct a backtrack-free parser for this expression grammar? So if you see, if the current non-terminal symbol to expand, let's say if this is our parse tree, okay, so this is our parse tree, so the current non-terminal symbol is the current leftmost non-terminal symbol to expand is E, then there is only one substitution rule that you can apply. So you just try it. That is E goes to T prime. But on the contrary, if the current substitution, if the current non-terminal symbol to expand is E prime, then there are 3 possibilities: plus, minus, and this is plus TE prime or minus TE prime or epsilon. So if the next input symbol is plus, then you want to use the first substitution rule. If the next substitution, if the current input symbol or the current look ahead symbol is minus, then you want to use the second substitution rule. But it is not clear when do we use the third substitution rule, that is E prime goes to epsilon. Okay, so that's an important question. Similarly, the case if the current non-terminal symbol to expand, if it is T, then no problem. Okay. Okay, so from here you U T alpha. If the current non-terminal, this is the non-terminal symbol you would like to expand in order to go to the next step of derivation process. So this is not a problem because T has only one possible substitution rule. So great, you go ahead and apply. But on the contrary, if the current non-terminal symbol is T prime, then it depends on what is the input symbol. So U, A, V. If the current input symbol A, if this is equal to star, then we can use the substitution rule. This is the substitution rule that you may want to use. But on the contrary, if the current input symbol A is this division operator, you want to use this substitution. But then again, the question is, when do you want to use the third substitution rule? t prime goes to epsilon. Okay, so that's a question that we have to answer. So now let's look at, this is a slightly expanded version of the previous grammar that we have seen. Earlier, a factor can be an expression within parentheses, or it can be an identifier. These are the only two possibilities. Now we are saying a factor can be an array index expression. A factor can be an array access or a function call. So now, like for example, now let's say, so starting from E in 0 or more steps, so you have something like UF alpha. This is the intermediate form that got generated. So now F is the non-terminal symbol that we would like to expand. And let's say the input symbol is, the input is like this, U, ID, V. Okay, this is the current input symbol. So now the current input symbol is ID, and if you look at the possible alternatives for alternate production rules for the non-terminal symbol F, there are three possibilities. Either you can use the first substitution rule, the second substitution rule, or the third substitution rule, or the fourth substitution rule. So here, one lookahead symbol is not sufficient in order for us to deterministically pick one of the three possible substitution rules. So we can possibly use two lookahead symbols. So that's an easy problem to solve. But then there is a bigger problem if you see this expression list. Let's say on the contrary, so the current non-terminal symbol to expand is this. Okay, the current non-terminal symbol to expand. Okay, the current non-terminal symbol to expand is this. So you start from E, and you have generated U already. You have E list non-terminal symbol followed by some string of terminal and non-terminal symbols. So E list is the current non-terminal symbol, and so what is E list? E list says E list is either an expression or a comma separated list of expressions. So if you see the input W, U, and then so U, A, V, this is the current input symbol. By looking at the current input symbol, we will not know whether the expression list that is there in the input stream, whether is it a single expression or is it a one, or is there two expressions, or there are three expressions, so on and so forth. So we have to go forward and see if there is a comma or not. Depending on that, we have to use either this substitution rule or this substitution rule. So again here the problem is, no matter how many lookahead symbols that we use, we will not be able to deterministically pick whether we should be using the first substitution rule for E list or the second substitution rule for E list, because we don't have control on the length of the expression. Let's say if you are using three lookahead symbols, let's say k is equal to 3. So, but then, like for example, but the input stream is like this. This is the input. And so U is what is generated. And then if you are using three lookahead symbols, then it could be the case, like, so 3 star, 4 star, L, comma, K star M. So if you use just three lookahead symbols, you will be able to see only till the symbol 4. But unless you see a little bit further, you don't know that, like there is one more expression in the expression list. So that's a problem. So these are the two problems in this grammar in order to come up with a backtrack-free parser. Because no matter how many lookahead symbols that we use, we are not able to resolve the choice between whether we should be using the substitution rule 1 or substitution rule 2 when it comes to the non-terminal symbol E list. But on the contrary, if you see the rules, these three rules, these are relatively easy to handle. Okay, you can just have two lookahead symbols and be able to say I can just go ahead and use either the substitution rule simply ID, or the array access substitution rule, or the function called substitution. So how do we handle this problem? So again, we rewrite the grammar, okay? And so how do we rewrite the grammar? So if you see these three substitution rules, which are causing us problem, they are causing us problem because they have a common prefix or a common prefix factor, that is ID. So you take this common prefix factor ID, and then the rest of the uh, entities, okay, that after you extract the common prefix, so whatever the things that they are, each of the substitution rules that are doing, we handle it by using a different non-terminal symbol. Like for example, here, if you see, so these four substitution rules, they are rewritten like this. The first option, it doesn't have any common factor with the other three substitution rules, so it remains as it is. The next three substitution rules, where they have a common factor, okay, we merge them into one production, that is ID followed by args. What is args? Args can be a null symbol which leads to the simple identifier, or it can be expression list within parentheses that leads to a function call, or it can be an expression list within square brackets which leads to array access. And then how do we handle this E-list, the problem that we are facing here with respect to E-list? So what we do again here is we do this left factoring transformation. So E is the common prefix for these two substitution rules. So we say E list is leads to E followed by E list prime. And what is E list prime? E list prime can be an epsilon symbol, or it is comma followed by E list. Okay. So by using this left factoring transformation, we will be able to take a grammar which is not amenable for backtrack-free parsing and convert it into a new form, which is no, which we can parse using a backtrack-free approach. So this grammar transformation is called as left factor. So many times when we want to apply a top-down, when we want to use a top-down parsing approach, so these are the two things that you may want to do. Number one, so you see, take care of left recursion. Okay, you may want to transform the grammar so that left recursion is eliminated, and that's what the grammar that we are seeing on the slide is obtained after eliminating the left recursion from the original grammar we started with. Remember, the original grammar we started with is E goes to E plus T, E minus T, blah. Okay, sort term. So this is the grammar which we started with. So that grammar got transformed into this after eliminating left recursion. And from here, we moved to here after by doing the left factoring transformation. So the final grammar that we have here is amenable for backtrack-free parsing. And the good thing about eliminating left recursion and even left factoring is you can algorithmically apply these transformations. There are algorithms, you can write an algorithm which takes a grammar as input and checks if there is left recursion in it. And if there is left recursion in it, it can automatically rewrite the grammar by eliminating the left recursion. Similarly, it is possible for us to take a grammar and see if there are problems that such as this, and it can rewrite the grammar, and so that so that the resulting grammar has no common prefixes among the substitution rules. So this is a general algorithm. So if you have something like there are two substitution rules with common prefix, A goes to alpha beta 1 or A goes to alpha beta 2. Alpha is the common prefix. So you take the common prefix out. This is the left factor grammar. So A goes to alpha A prime, and A prime can be beta 1 or beta 2. So if there is a common prefix, you cannot design a backtrack-free parser, because like you might be able to generate a prefix of the leftover string either be using the first substitution rule or second substitution rule. So we don't have a hope of coming up with a backtrack-free parser if we have substitution rules such as this. So we have to left factor the grammar. So this is a general algorithm. You may want to look at it later. Yeah, so there are a couple of examples. So again, this example, I would like you to take this example and first remove the left recursion in this grammar because this grammar is not amenable for top-down parsing. And then after removing the left recursion, apply the left factoring transformation and generate the new graph. This is an example I would like you to work in your rooms. So this is yet another example. So again, there is left recursion in it, remove the left recursion, and after removing the left recursion, see if you have to do left factoring. So with this, so after you do all these transformations, so we want to come up with a approach to construct a backtrack-free parser by using the lookahead symbols in a very systematic fashion. So we have what are called as L10 grammars. Okay, so just to recall, the problem that we have at hand is so we are given a leftmost non-terminal symbol in the parse tree. So we have, this is the parse tree that we have. Okay, so this is the leftmost non-terminal symbol, and so we want to expand A. There are two possible substitution rules. A goes to alpha 1 or alpha 2. And the question that we are asking is, can we use the next k tokens to determine whether we should be using the substitution rule 1 or 2? Grammars where such a thing is possible, they are called as LLK grammars. So if you recall the ideas from the automata theory course, or the ideas that we have seen before, the power of context-free grammars comes from non-determinism. That is, if you take a non-terminal symbol A, there are multiple possible ways in which that non-terminal symbol can unfold itself. Okay, so for example, if we have a non-terminal symbol statement, then the statement can be a while loop, or it can be a for statement, or it can be a do statement. So that is where this non-determinism is what gives the context-free grammars power. So now when we look at the machine equivalent of non-deterministic of context-free grammars, the machine equivalent of context-free grammars is push-down non-deterministic push-down automaton. Okay. So in order to simulate the non-determinism that is present in the context-free grammars, the push-down automata also needs to have this power of non-determinism. And but non-determinism is expensive because we don't have the ability of magically figuring out what is the right substitution rule to use, or what is the right transition the PDA should be using. Like for example, if you think of a non-deterministic PDA, okay, so let's say let's look at the transition function associated with if the current Q is the current state in which the PDA is in, the current input symbol is A, X is on the top of the stack, then there could be two possible states outcomes. Okay, like for example, the PDA can go to state P and then it can replace the stack X with alpha, or it can go to state R and then it can replace the stack symbol X with beta. Okay, so these are the two possibilities, let's assume. And in general, we can have more than two possibilities. So the non-deterministic PDA, mathematically speaking, like if there exists a particular choice of state transitions, which leads us to as an accepting state, then we say the NPDA accepts an input stream, right? But then, so we don't have that magic power of non-determinism. So in backtrack-free parsing, what we do is we beat non-determinism by trying out all possibilities. That is, by trying out all possible state transition functions here. Okay, but this is a bad choice because it will lead to parsers whose time complexity is could be exponential. Okay, so we don't want so we want to beat non-determinism. Okay, but at the same time, NPDs are not equal to DPDs. They are not equivalent to DPD. So what do we do? So the idea is we want to use the current the input symbol. So we want to use the current lookahead symbol and use that extra information to beat non-determinism. So as I have explained before, so checking if the next input symbol, if the next token is a for token, then among the available substitution rules for the statement, we may want to use the substitution rule associated with the for statement. So we want to use the next look ahead symbol to beat non-determinism. And it is possible for some grammars, it is possible, and in some cases, it's not possible. Grammars in which this is possible, they are called as LLK grammars. Grammars in which we can eliminate or we can beat non-determinism by using the next K lookahead symbols, they are called as LLK grammars. So in general, given an arbitrary grammar, we don't know whether it is possible for us to construct a backtrack-free grammar for the same grammar in an algorithmic approach. It's an undecidable problem. Okay, it's an undecidable problem. So what does each of the things in LL1 stand for? So the first L in LL1, it says that we are scanning the input from left to right. And the second L here, it stands for that we are scanning the input, we are constructing a leftmost derivation for an input string. And the one here stands for that we are using one symbol look ahead. So all right, I will stop here and we will take up the idea of the topic of LL1 parsing in the next class. Okay, so this is the basis, and in the next class we will see the whole theory of LL1 parsing. And if you have any questions, you can ask me now.